right, ladies and gentlemen, welcome back to another round of AP Chemistry. Today we're going to be taking a look at equilibrium. This is something that you probably remember or recall from your pre-AP days, but I want to make sure that you got it down, so I'm going to purposefully take you through some stuff that I expect you to know. The first thing is what equilibrium actually is. All right, so Equilibrium exists when the rate of the forward reaction is equal to the rate of the reverse reaction. So it exists when the rate of the forward reaction is equal to the rate of the reverse reaction. And by rate, what we're talking about here is essentially how fast this thing is going to go. All right, this really is how fast, right? When the speed of the forward reaction equals the speed of the reverse reaction, we are at what we call equilibrium. So if I have a general, very simple equation, what I'm talking about here is that as A disappears, D is produced, but then at the same time, you need to understand when you look at a reaction, there's directionality to it. I've got forward and I've got reverse, because what's to say that when D is produced, that it's not going to form A. And so that's kind of that mind shift that we have to make sure that we understand and that we're familiar with when we're talking about equilibrium. So let's take a look at a graph of what I am talking about here. So specifically, if I'm going to use A as my red, then if my axes here are concentration versus time, I've got a concentration versus time graph here, what would we expect A to look like as the reaction went on? Well, it would actually decrease over time, right? And notice it levels out there at some point. So A is going to decrease because at the beginning of the reaction, right, we've got all A there. It's actually going to start disappearing, so we would expect the concentration to decrease. Nothing too crazy there. Now what we see with D is we see that as A disappears, D will actually increase. Now notice the slope of these graphs, right? You notice, and I tried to purposefully do this to where A is slowly decreasing, but D, the appearance of D is actually faster, and it should make sense because of the coefficients here. D should appear twice as fast as A disappears, right? And that's why stoichiometry and balancing these equations is so important, because it'll tell us, right, what rate this thing is actually, or it won't tell us, but it'll give us some inclination into what rate this is actually going to appear and disappear at, all right? Now, I do want to point out one very specific point here, right? And that's when my lines both actually level out. And what we do is we call this point equilibrium, right? At equilibrium, so here we are at equilibrium. At equilibrium, the concentrations aren't changing anymore. And again, this is talking about that rate, because for every A that disappears, I get 2D that are produced, but then I also get 2D that break down and form an A. And so it's like moving marbles from a jar, right? If I move 2 marbles over to the right, but then at the same time I move 2 marbles over to the left, to form 1A, there's no net change at that point, all right? And so what we need to understand, and this is something I'm not going to write, but I need you to write it, is that at equilibrium we have a specific ratio of concentrations, right? And so we have a ratio of the concentration of products over a ratio of the concentration of the reactants. And that at equilibrium, notice these lines flatten out, and that ratio does not change. So at equilibrium, we do have that very specific ratio, right? And then another thing to understand is that the slope of these lines is, right, it is dependent on coefficients. And so what we do at equilibrium is we come up with an equilibrium constant that we use capital K for, and what we're going to say is that this is going to be equal to the concentration of the products over the concentration of the reactants, right? And it's because of that state where the concentrations aren't changing that we can get this equilibrium constant, right? For our reaction specifically, because there are coefficients and we do need to come into coefficients, so I guess I could put, N and M there as exponents. And so literally to write the equilibrium expression for what we've got, we would say D squared over the concentration of A. Because remember, equilibrium expressions are products over reactants. Coefficients become exponents, all right? And so important that you get that step down. Equilibrium expressions are products over reactants, and coefficients become exponents. The other thing that I will add here and remind you of is that we never include pure substances, which are solids or liquids in our equilibrium expression. So we will never include solids or liquids in our equilibrium expression. All right? So to write an equilibrium expression, products over reactants, coefficients become exponents, and we were going to leave out the solids and the liquids. Okay? All right, and so what I did is I went ahead and I erased the page there, and I wrote this statement: all reactions move towards equilibrium. All right, and so that's something that we want to take a look at, because whether or not, like, equilibrium is that perfect ratio of products over reactants, and if I'm not there yet, then what's going to happen is the reaction will actually naturally move towards that point. And so I'm going to look at a couple of different scenarios. First thing, I'm going to introduce a variable called Q, and Q is called the reaction quotient. And what this does is it takes a look at this ratio of products to reactants when I'm not at equilibrium. All right? And so I've got a couple of different scenarios here. The first one, what if I have I've got too much product? What does that mean? So if I look at my equilibrium expression, d squared over concentration of A, what that means is that this is going to be too large. So I'm not at equilibrium, right? And so what I'm going to do is I will actually say that this is now equal to Q, not equal to K, and that in this particular case, the Q value is greater than the K value. And so again, that statement, all reactions move towards equilibrium, in this particular case, I've got my reverse reaction that will be favored. So reverse reaction favored. And in that particular case, the D would be consumed and A would be produced. So I would have to decrease the amount of D and increase the amount of A. And what that does is that brings my ratio down towards K. All right? And so too many products, the top of my fraction is too large. I've got to get rid of some product. I'm going to produce A, so I'm moving primarily in the reverse reaction direction. Now, the other scenario that we're going to take a look at is what happens when we have too much reactant. So if I have too much reactant, what happens again, I'm looking at this same equilibrium expression, right? And in this particular case, my value will be my ratio will be too small. So again, this is Q equals to that equilibrium expression because I'm not at equilibrium. I don't have that ratio, right? And so in this particular case, I'm going to say Q is less than K. And in that particular case, you have to understand, if I'm going to be moving towards equilibrium, then I've actually got to get rid of my reactants and produce products. And so in this particular case, we would say that my forward reaction is favored, right? And so there my forward reaction is favored, and so A would be consumed and D would be produced. And then I guess the third situation that I might have maybe wanted to start with is when Q is equal to K, we are at equilibrium. And neither direction of the reaction is favored. They're both still occurring, but they're occurring at the same rate. All right? Okay. And so, because some of the takeaways from this that you want to make sure you walk away from is the understanding of how to write the equilibrium expression, and then also the understanding of what do we do when we're not at equilibrium, right? How do we determine? We can actually put these concentration of products over concentration of reactants and figure out and compare this to a known K value, and then just say, hey, is my Q value too large or too small, right? And that tells us which direction the reaction will go. All right, but if they are equal, we are at equilibrium, and we can just assume that there will be no change in concentrations at that point. Okay? All right, ladies and gentlemen, that's it. Hopefully you got all your questions answered. If you didn't, please write them down. Please bring them to class. We'll talk about them, or you can come to tutorials. You get some one-on-one time, and we'll actually talk about them there. All right? I will see you there.